Hello friends, in everyday language, the term sequence means a succession of things in a definite order. The order may be chronological order, size order, logical order, etc. In mathematics, the term sequence is commonly used to denote succession of numbers whose order is determined by a rule or a function. We encounter sequence at the very beginning of our mathematical experience. The list of even numbers 2, 4, 6, 8, etc. and the list of odd numbers 1, 3, 5, 7, etc. are examples. We can predict what is the 20th term of each sequence by observing the pattern. Another sequence of great historical interest is the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, etc. in which each term is the sum of the two preceding terms except the first two terms. For instance, 8 equal to 3 plus 5, 13 equal to 5 plus 8, etc. In this case, it is somewhat more difficult to predict the 20th term without listing all the previous ones. We discuss more about Fibonacci sequence shortly. A sequence can be thought of as a list of elements with a particular order. Sequence is an enumerated collection of objects in which repetitions are allowed. Like I said, it contains members also called elements or terms. In contrast to sets, the same element can appear multiple times at different position in a sequence, but order matters. Sequences are useful in number of mathematical disciplines for studying functions, spaces and other mathematical structures using the convergence properties of sequences. Apart from the crucial role in mathematics, sequences have many useful applications in areas such as finance, physics and statistics. For example, we can invest ₹1000 at an interest rate of 5% per annum, compounded annually, and list the sequence consisting of all the values of the investment each year ₹1000, ₹1050, ₹1102.50, ₹1157.63, ₹1215.51, etc. These amounts are rounded to the nearest paise. For a given sequence, we can ask the questions. Can we find a formula for the general form of the sequence? Does the sequence have a limit? That is, do the numbers in the sequence get as close as we like to some number? In this session, we try to answer these questions. We begin with a formal definition of a sequence. Sequences. If to each positive integer n, there is assigned a real or complex number un, then these numbers u1, u2, etc., un, etc. are said to form an infinite sequence, or briefly a sequence, and the numbers un are called the terms of the sequence. More precisely, a sequence of real numbers or a sequence in R is a function from the set n equal to set 1, 2, etc. of natural numbers to the set R of real numbers. A sequence whose terms are real numbers is called a real sequence. In our course, we consider only real sequences. Being a function from the set of natural numbers to the set of real numbers, a sequence in R assigned to each natural number n equal to 1, 2, etc. a uniquely determined real number. The real numbers so obtained are called the terms of the sequence. It is customary to denote the element of R assigned to n belong to n by a symbol such as un or an or xn, and is called the nth term of the sequence. Thus, if u is a function from natural number into real number, is a sequence we shall ordinarily denote the values of u at n by un rather than by u of n. We will denote the sequence by the notation sequence un or by or set of all un such that n belongs to n. For example, the sequence of positive integer multiples of 5, namely 5, 10, 15, 20, etc. can be expressed by the function u from set of all natural number to set of all real number defined by u of n equal to 5n. That is, the sequence is sequence un, where un equal to u of n, which is equal to 5 times n. In a sequence, the order of elements is important in contrast to this set, where the elements have no specific ordering. For example, the sequence negative 1 power n, n belongs to natural number, is sequence negative 1, 1, negative 1, 1, etc., and alternates between negative 1 and positive 1. Whereas the set sequence negative 1 power n, n belongs to natural number n, is equal to the set negative 1, 1, consisting of only 2 elements. Remember that in set being a collection of distinct objects, elements are not repeated. Consider a sequence defined by u of n equal to n plus 1 upon n. Here the first term is u of 1 equal to 2, second term is u of 2 equal to 3 upon 2, third term is u of 3 equal to 4 upon 3, and so on. The nth term is u of n equal to n plus 1 upon n. When we use the subscript notation un for u of n, the sequence is written u1 equal to 2, u2 equal to 3 upon 2, u3 equal to 4 upon 3, etc., un equal to n plus 1 upon n. Or simply by notation u of n equal to sequence n plus 1 upon n. Some other examples of sequence are sequence un equal to sequence of square root of n, sequence un equal to sequence of negative 1 power n plus 1 times 1 upon n, sequence un equal to sequence of n upon n plus 1. The nth term of the sequence square root of 2, square root of 3, square root of 4, etc., is un equal to square root of n plus 1, and the sequence is denoted by sequence un equal to sequence of square root of n. The nth term of the sequence 1, 1 upon 2, 1 upon 3, etc., is un equal to 1 upon n, and the sequence is denoted by sequence un equal to sequence 1 upon n. The nth term of the sequence 0, negative 1 upon 2, 2 upon 3, negative 3 upon 4, etc., is un equal to negative 1 power n plus 1 times n minus 1 upon n, and the sequence is denoted by sequence un equal to sequence of negative 1 power n plus 1 into n minus 1 upon n. Finally, the nth term of the sequence 5, 5, 5, etc., is un equal to 5, and the sequence is denoted by sequence un equal to sequence 5. This is an example of constant sequence. In general, if b is a real number, then the sequence b equal to sequence b, 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 etc., all of whose terms are equal to b, is called the constant sequence b. Thus, the constant sequence 1 is the sequence 1, 1, 1, etc., all of whose terms are equal to 1, and the constant sequence 0 is the sequence 0, 0, 0, etc. Graphs of sequences. Since sequences are functions, it makes sense to talk about the graph of a sequence. For example, the graph of the sequence un equal to sequence n is the graph of the equation y equal to n, n equal to 1, 2, 3, etc. Because the right side of this equation is defined only for positive integer values of n, the graph consists of a succession of isolated points. This is different from the graph of y equal to x, x greater than or equal to 1, which is a continuous curve indicated by red color. Graph of the sequence un equal to sequence n upon n plus 1 in blue color, and the graph of the function y equal to x upon x plus 1 as x greater than or equal to 1 in red color are given together in figure. Limit of a sequence. Since sequence are functions, we can inquire about their limits. However, because a sequence un is only defined for integer values of n, the only limit that makes sense is the limit of un as n approaches positive infinity. By observing the graph of the sequence n, it can be seen that the terms of the sequence increase without bound. From the graph of the sequence negative 1 power n, we observe that the terms oscillates between negative 1 and positive 1. By looking at the graph of the sequence n upon n plus 1, we see that the terms approach a limiting value of 1. Informally speaking, the limit of a sequence un is intended to describe how un behave as n approaches to positive infinity. To be more specific, we will say that a sequence un approach a limit L if the terms in the sequence eventually become arbitrarily close to L. Geometrically, this means that for any positive number epsilon, there is a point in the sequence after which all terms lies between the line y equal to L minus epsilon and y equal to L plus epsilon. This is illustrated in figure. The precise definition of limit of a sequence of real numbers follows. A sequence un is said to converge or to be convergent if there is a number L with the following property. For every epsilon greater than 0, there is a positive integer n such that absolute value of un minus L less than epsilon for n greater than or equal to n. In this case, we say that L is the limit of the sequence. Then we write limit of un as n approaches infinity is L, or simply un approaches L as n approaches to infinity, and say that the sequence converges to L or has a limit L. If no such L exists, we say that sequence un diverges. Note that for a sequence un to converge to some limit L, it is needed that after some stage or index, all the terms of the sequence should be very close to L. As an example, we show that limit of 1 upon n as n approaches infinity is 0. Here the nth term of the sequence is un equal to 1 upon n, and to show that the limit L equal to 0. For this, let epsilon greater than 0 be given. We must show that there exists an integer n such that n greater than or equal to n implies absolute value of un minus L less than epsilon. That is, to show that there exists a positive integer n such that absolute value of un minus L less than epsilon for n greater than or equal to n. That is, such that absolute value of 1 upon n minus 0 less than epsilon for n greater than or equal to n. That is such that 1 upon n less than epsilon for n greater than or equal to n, equation 1. Now, we cannot proceed further without stating the Archimedean property, named after the ancient Greek mathematician Archimedes, 287 BC to 212 BC of Syracuse. The Archimedean property is that if x is a real number, then there exists a natural number n such that x less than n. This n depends on the choice of x. Now, let us continue the work of finding an n satisfying the condition 1. The Archimedean property assures us the existence of a natural number n associated with a real number 1 upon epsilon such that n greater than 1 upon epsilon, then 1 upon n less than epsilon. And hence it follows that 1 upon n less than or equal to 1 upon n less than epsilon for n greater than or equal to n. Hence, 1 upon n less than epsilon for n greater than or equal to n, equation 1 as desired. This proves that limit of 1 upon n as n approaches infinity is 0. As another example, if k is a real number, we show that limit of k as n approaches infinity is k. Let epsilon greater than 0 be given. We must show that there exists a positive integer n such that absolute value of k minus k less than epsilon for n greater than or equal to n. Since k minus k equal to 0, we can use any positive integer for n and the above statement will hold. This proves that limit of k as n approaches infinity is k for any constant k. Now, we show that the sequence 3, 2, 5 upon 3, 6 upon 4, 7 upon 5, etc. 1 plus 2 upon n, etc. is convergent and has a limit L equal to 1. The nth term of the sequence is un equal to 1 plus 2 upon n and L equal to 1. Let epsilon greater than 0 be given. We must show that there exists a positive integer n such that absolute value of un minus L less than epsilon for n greater than or equal to n. that is such that absolute value of 1 plus 2 upon n minus 1 less than epsilon for n greater than or equal to n. That is such that 2 upon n less than epsilon for n greater than or equal to n, equation number 2. That is, depending on epsilon greater than 0, if we choose a positive integer n such that n greater than or equal to 2 upon epsilon, then the statement 2 holds. So, sequence un converges to 1. The n epsilon game. The way of finding a natural number n corresponding to a given epsilon greater than 0 can be regarded as a game called n epsilon game. In this game, player A asserts that limit of un as n approaches infinity is L. In making this assertion, player A is issuing a challenge to player B to give a specific value for epsilon greater than 0, after which player A will provide a natural number n equal to n epsilon, that is a natural number n depending on epsilon, such that if n is a natural number and n greater than or equal to n, it will be true that absolute value of un minus L less than epsilon. If player A can always come up with a value of n equal to n epsilon and show that this value will work, he wins. Then limit of un as n approaches infinity is L is true. However, if player B can give a value of epsilon greater than 0, for which player A fails to give an accurate response, then player B wins. Then limit of un as n approaches infinity is L is false. For example, as observed in an earlier example, in proving limit of 1 upon n as n approaches infinity is 0, player A can always come up with a natural number n greater than 1 upon epsilon corresponding to a value of epsilon greater than 0 given by player B. As another example, we use the game to show that the sequence 0, 2, 0, 2, etc., 0, 2, etc. does not converge to 0. If player A asserts that 0 is the limit of this sequence, he will lose that n epsilon game when player B picks a value of epsilon less than 2. To be definite, let player B choose epsilon equal to 1, then no matter what value player A picks for n equal to n of 1, his response will not be adequate. For player B can always select an even number n greater than n, for which the corresponding value un equal to 2, and for which absolute value of un minus 0 equal to absolute value of 2 minus 0 equal to 2 greater than 1. Thus, the number 0 is not the limit of the sequence un. We also observe that the sequence 0, 2, 0, 2, etc., 0, 2, etc. does not converge to any real number, because the terms of the sequence are alternatively 0 and 2, and hence they never accumulate near any unique value. Therefore, the sequence diverges. We now show that sequence negative 1 power n plus 1 into n minus 1 upon n diverges. Take a positive epsilon smaller than 1, so that the bands shown in figure 1 about the line y equal to 1 and y equal to negative 1 do not overlap. Any epsilon less than 1 will do. Convergence to 1 would require every point of the graph beyond a certain index n to lie inside the upper band. But this will never happen. As soon as the point ordered pair n a n lies in the upper band, the next point ordered pair n plus 1 a n plus 1 will lie in the lower band. Hence, the sequence cannot converge to 1. Likewise, it cannot converge to negative 1. On the other hand, because the terms of the sequence get alternatively closer to 1 and negative 1, they never accumulate near any other value. Therefore, the sequence diverges. The sequence square root of n diverges because it outgrows every real number L. To describe the behavior of sequence of square root of n, we write limit of sequence of square root of n as n approaches infinity is infinity. In speaking of infinitely as a limit of sequence un, we mean that un become numerically large without any bound as n increases. We now discuss an important sequence in mathematics literature, namely the Fibonacci sequence. In 1202. Italian mathematician Leonardo Pisano, also known as Fibonacci, pondered the question, given optimal conditions, how many pairs of rabbits can be produced from a single pair of rabbits in 1 year? This thought experiment dedicates that suppose that our rabbits never die. The female rabbit always give birth to pairs and each pair consists of one male and one female. Think about it. Two newborn rabbits are placed in a fenced-in yard and left to well breed like rabbits. Rabbits can't produce until they are at least 1 month old. So, for the first month only one pair remains. At the end of the second month, one female gives birth, leaving 2 pairs of rabbits. When month 3 rolls around, the original pair of rabbits produces yet another pair of newborn, while their earlier offspring grow to adulthood. This leaves 3 pair of rabbits, 2 of which will give birth to 2 more pairs the following month. The order goes as follows: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, etc. Each number from third position is the sum of the previous 2. This series of number is known as the Fibonacci numbers or the Fibonacci sequence. The ratio between the numbers 1.618034 is frequently called the golden ratio or golden number. At first glance, Fibonacci's experiment might seem to offer little beyond the words of speculative rabbit breeding, but the sequence frequency appears in the natural world, a fact that has intrigued scientists for centuries. For instance, on many plants, the number of petals is a Fibonacci number. Buttercups have 5 petals, lilies and iris have 3 petals, some delphinium have 8, corn marigolds have 13 petals, some asters have 21, whereas daisies can be found within 34, 55 or even 89 petals. While describing the Fibonacci sequence, we have observed that first 2 elements are the number 1. Each number from third position is the sum of the previous 2. So, mathematically, we can describe this as follows. The Fibonacci sequence f equal to sequence fn is given by the statements f1 equal to 1, f2 equal to 1 and fn plus 1 equal to fn minus 1 plus fn for n greater than or equal to 2. This way of defining a sequence, calculating the next term of the sequence from previous terms via some formula is known as the recursive definition of the sequence. Using the recursive definition, we can list the first few terms of the Fibonacci sequence as f equal to sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. The Fibonacci sequence diverges because it outgrows every real number L. To describe the behavior of f equal to sequence fn, we write limit of sequence fn as n approaches infinity is infinity. Subsequences. A subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. The following are subsequence of the sequence 1, 2, 3, 4, 5, etc. and etc. of integers. First one, the subsequence of odd integers 1, 3, 5, etc. 2n minus 1, etc. Second one, the subsequence of even integers 2, 4, 6, etc. 2n, etc. Third one, the subsequence of primes 2, 3, 5, 7, 11, etc. But 3, 7, 5, 1, etc. is not a subsequence of the given sequence because the terms do not appear in the given order as in the original sequence. Some subsequence of x equal to sequence 1 upon 1, 1 upon 2, 1 upon 3, etc. are sequence 1 upon 1, 1 upon 3, 1 upon 5, etc., 1 upon 2n minus 1, etc. and sequence 1 upon 2 factorial, 1 upon 4 factorial, etc., 1 upon 2n factorial, etc. But y equal to sequence 1 upon 2, 1 upon 1, 1 upon 3, etc. is not a subsequence of x because the terms of y do not appear in x in the given order. the concept of subsequence have some role in determining whether a sequence converges or not. We have the following observations. First one, if a sequence un converges to L, then all of its subsequences converges to L. We use this to show that the sequence negative 1 power n is divergent. If the sequence negative 1 power n were convergent to a number x, then every subsequence of it must converges to x. But the subsequence negative 1, negative 1, negative 1 etc. of odd numbered terms converges to negative 1, while the subsequence 1, 1, 1 etc. of even numbered terms converges to positive 1, a different limit. Second one, if any subsequence of a sequence un diverges, then sequence un diverges. For example, the sequence 1, 0, 2, 0, 3, 0 has a divergent subsequence, namely 1, 2, 3 etc. So, the sequence 1, 0, 2, 0, 3, 0 etc. diverges. Third one, if two subsequences of a sequence un have different limits, then sequence un diverges. For example, for the sequence 0, 2, 0, 2 etc., 0, 2 etc., the subsequence 0, 0, 0 etc. converges to 0, while the subsequence 2, 2, 2 etc. converges to 2. Also, the sequence 0, 2, 0, 2 etc., 0, 2 etc. diverges. Definition: a tail of a sequence is a subsequence that consists of all terms of the sequence from some index n onwards. In other words, a tail is one of the sequence un such that n greater than or equal to n for n equal to 1, 2, 3 etc. Definition: if x equal to sequence u1, u2 etc. un etc. is a sequence of real numbers, and if m is a given natural number, then the m tail of x is the sequence xm equal to sequence um plus 1, um plus 2 etc. and its nth term is um plus n. For example, the third tail of the sequence x equal to sequence 2, 4, 6, 8, 10 etc. 2n etc. is the sequence x3 equal to sequence 8, 10, 12 etc. 2n plus 6 etc. In terms of tail of a sequence, a way to say that un approaches to L is to say that for every epsilon greater than 0, the epsilon open interval L minus epsilon, L plus epsilon about L contains a tail of the sequence that are bounded from above. Definition: a sequence un is bounded from above if there exists a number m such that un less than or equal to m for all n. The number m is an upper bound for sequence un. If m is an upper bound for sequence un and no number less than m is an upper bound for sequence un, then m is the least upper bound or supremum for sequence un and is denoted by m equal to supremum of sequence un, n belongs to the set of all natural numbers. The sequence 1, 1 upon 2, 1 upon 3 etc., 1 upon n etc. is bounded from above by 1. Also, 1 is the least upper bound. As another example, the sequence 1, minus 1, 1, minus 1 etc. minus 1 power n plus 1 etc. is bounded from above with an upper bound 1. 1 is the least upper bound as no number less than 1 is an upper bound. Also note that any real number greater than or equal to 1 is also an upper bound. Bounded non-decreasing sequences. Definition: a sequence un with the property that un less than or equal to un plus 1 for all n is called a non-decreasing sequence or an increasing sequence. Some examples of non-decreasing sequence are: first one, the sequence 1, 2, 3 etc. n etc. of natural numbers. Second one, the sequence 1 upon 2, 2 upon 3, 3 upon 4 etc. n upon n plus 1 etc. Third one, the constant sequence 5. There are two kinds of non-decreasing sequence: those whose terms increase beyond any finite bound and those whose terms do not. A non-decreasing sequence that is bounded from above always has a least upper bound. This fact is a consequence of the completeness property of real numbers, but we will not prove it here. Completeness property of real numbers states that every non-empty set of real numbers that has an upper bound has a least upper bound in the set of real numbers. As an example, the non-decreasing sequence 1 upon 2, 2 upon 3, 3 upon 4 etc. n upon n plus 1 etc. is bounded from above by 1. No number less than 1 is an upper bound for the sequence. So, 1 is the least upper bound. The non-decreasing sequence 1, 2, 3 etc. n etc. has no upper bound and hence no least upper bound also. The following results whose proofs is omitted ensures us that if L is the least upper bound of a non-decreasing sequence of real numbers, then the sequence converges to L. Theorem, the non-decreasing sequence theorem. A non-decreasing sequence of real numbers converges if and only if it is bounded from above. If a non-decreasing sequence converges, it converges to its least upper bound. For example, 1 is the least upper bound of the non-decreasing sequence 1 upon 2, 2 upon 3, 3 upon 4 etc. n upon n plus 1. Also the sequence converges to the least upper bound 1. Sequence that are bounded from below. Definition: a sequence un is bounded from below if there exists a number m such that m less than or equal to un for all n. The number m is a lower bound for sequence un. If m is a lower bound for sequence un and no number greater than m is a lower bound for sequence un, then m is the greatest lower bound or infimum for sequence un and is denoted by m equal to infimum of sequence un, n belongs to natural number. The sequence 1, 1 upon 2, 1 upon 3 etc., 1 upon n etc. is bounded from below by 0. Also 0 is the greatest lower bound. As another example, the sequence 1 minus 1, 1 minus 1 etc. minus 1 power n plus 1 etc. is bounded from below with a lower bound negative 1. Negative 1 is the greatest lower bound as no number greater than negative 1 is a lower bound. Also note that any real number less than or equal to negative 1 is also a lower bound. A sequence is said to be bounded if it is both bounded from above and bounded from below. For example, 1 negative 1, 1 negative 1 etc. negative 1 power n plus 1 etc. is bounded neither 1, 2, 3 etc. n etc. nor negative 1, negative 2, negative 3 etc. negative 1 etc. is bounded. Bounded non-increasing sequences. Definition: a sequence un with the property that un greater than or equal to un plus 1 for all n is called a non-increasing sequence or a decreasing sequence. Some examples of non-decreasing sequence are: first one, the sequence negative 1, negative 2, negative 3 etc. negative n etc. of natural numbers. Second one, the constant sequence 5. There are two kinds of non-increasing sequences: those whose terms decrease beyond any finite bound and those whose terms do not. A non-increasing sequence that is bounded from below always has a greatest lower bound. This fact is also a consequence of the completeness property of a real numbers. As an example, the non-increasing sequence negative 1 upon 2, negative 2 upon 3, negative 3 upon 4 etc., negative n upon n plus 1 etc. is bounded from above by negative 1. No number larger than negative 1 is a lower bound for the sequence. So, negative 1 is the largest lower bound. The non-decreasing sequence negative 1, negative 2, negative 3 etc., negative n etc. has no lower bound and hence no greatest lower bound also. The following result ensures us that if L is the least upper bound of a non-decreasing sequence of real numbers, then the sequence converges to L. Theorem, the non-increasing sequence theorem. A non-increasing sequence of real numbers converges if and only if it is bounded from below. If a non-increasing sequence converges, it converges to its greatest lower bound. For example, negative 1 is the least upper bound of the non-decreasing sequence negative 1 upon 2, negative 2 upon 3, negative 3 upon 4 etc., negative n upon n plus 1 etc. Also the sequence converges to the greatest lower bound negative 1. A sequence is said to be monotone if it is either an increasing sequence or a decreasing sequence. With this new definition, we have the following important theorem. Theorem, monotone convergence theorem. A monotone sequence of real numbers is convergent if and only if it is bounded. Further, first one, if sequence xn is bounded increasing sequence, then limit of xn equal to supremum of sequence xn, n belongs to natural number n. Second one, if sequence yn is bounded decreasing sequence, then limit yn equal to infimum of sequence yn, n belongs to natural number n. As an example, consider the sequence 1 upon square root of n, that is bounded below by 0 and above by 1. Hence, it is bounded. Also, it is decreasing. Hence, by part B of the monotone convergence theorem, limit of 1 upon square root of n equal to infimum of sequence 1 upon square root of n, n belongs to natural number. As 0 is the infimum for the set sequence 1 upon square root of n, n belongs to natural number, it follows that limit of sequence 1 upon square root of n is 0. Let us summarize the session. In this session, a particular function sequence with a set of natural numbers as domain have been described. Being a function, we could discuss the graph and limit of sequences. The idea of subsequence is introduced and examine how the behavior of these subsequence can be used to conclude the convergence or divergence of the original sequence. We observe that some sequences are increasing or decreasing, and if such sequences are bounded, then they are convergent. In that case, limits can be found easily by determining supremum or infimum of the sequences. Hope you all enjoy the session. See you next time. Until then, goodbye.